Very good afternoon, everyone. I welcome you all in the post-lunch session of the day. And in this session, Professor Kale will continue his discussion on applications of silicon nanodots in the field of hydrogen storage. So, sir, I hand over the session to you.
Yeah, thank you very much. Let me share the screen. So is the screen visible and am I audible?
Yes, sir, you're perfectly audible and screen is also visible, sir.
Thank you very much. So in earlier part, we have seen how four different types of silicon nanostructures are produced. And at that time, the applications were like everything. So we talked about some aspects regarding all the applications, and then later we moved on silicon photovoltaics, where we talked about why we require to engineer the material, band gap, reduce the cost, how to reduce the cost, and how we can use the properties of silicon nanostructures to do that, and what are the possibilities as well. So that was one part, energy conversion. And of course, we know that for renewables, we also require a the storage as well. That is the very intrinsic problem of renewables, right? So we do not have inherent storage characteristics in them. So of course, for storage, we have many other things like battery, hydrogen storage is upcoming. And then there are very established methods for the storage, established materials as well. But then we thought that the silicon, because our the center of my research is about silicon, so we are trying all these things, and then we understand that silicon is already used in microelectronics, and then there is one method called as passivation, where we coat the silicon using some hydride. So we make silicon hydride on the surface to increase the band gap, to even to decrease the defect. This passivation is helpful. So that was the idea when it occurred to me that silicon, why not silicon can be used for hydrogen. But then, of course, as I said, the problem with silicon for hydrogen storage is its surface area. So bulk silicon you cannot use. So anyway, we were trying quantum dots for silicon for hydrogen storage, and then now we have started using other nanostructures as well for that. So in this session, I'm going to talk about how these properties of silicon nanostructures can be exploited for the storage, and how we can choose which structure is the best and how. Of course, earlier I took 10 minutes extra, so this time I'm very sure that I will conclude well within time, and I think I'll save some time. So anyway, so coming to this silicon for hydrogen storage. So let us start with why is silicon for hydrogen storage, apart from the other advantages already I've talked about in the previous session. So here, as I've said, hydrogen has got quite good affinity towards the silicon, especially amorphous or whatever the form, amorphous, crystalline, or nano, whatever you take it as. And then the dissociation energy in silicon hydrogen bond is also higher as compared to the silicon bond. So it is expected that it will take a bit extra energy for silicon hydrogen to break. So silicon, of course, it has got valency 4, but SiH4 may not be practically viable. But even if we go with silicon hydrogen, still it will give around 3.44 mass percentage, maximum mass percentage, and it can be increased to 9.67 if we go for silicon trihydride, right? So this is very interesting, and these numbers, although they are theoretical, it looks promising. And then again, we know that silicon is established material, and when we recycle the silicon, that recycled silicon can also be used for hydrogen storage. So we may not have a large material cost over here. As far as, so that was all about absorption. Of course, you must have heard many people in this workshop that both the things are important, absorption as well as desorption, and that should be done at a relatively low temperatures and pressure. So expected about up to 10 bar and 200 degrees Celsius, that would be the very ideal material for hydrogen storage. And then what we found out that this hydrogen can be dissolved. The simplest method would be heating. hitting in between 200 to 600. So in these particular three bond, SiH, SiH2 and SiH3, they starts breaking, and you get the hydrogen back. So these looks very promising. And of course, as far as the increase is concerned in hydrogen uptake, we know that we have to increase the control size and surface area and everything. But when we go for very small, say quantum dots, or very small, very thin films, then the interesting thing is the hydrogen diffusion paths are shortened. It means hydrogen can go inside even that small grain of silicon or a small quantum dot, and it can sit inside. So for silicon hydrogen in 1:1 proportion, it will have a nanoparticle size of about 1 nanometer or less than that, and it can store about 3.4 by weight percent. So these are the interesting properties, especially when we talk about the silicon for hydrogen storage. So here, what are the factors that would be affecting the adsorption dissolution process? Of course, we have to start with the surface area. Now, this surface area is in a way controlled by pore size. And there is one more thing, pore size distribution. So pore size, so surface area is a function of pore size and pore size distribution. Then we have got crystallinity. Of course, in here, now we have to find out a compromise. We cannot have an amorphous material as such, because the decomposition, the deterioration of the material might be a problem. And of course, if it is too crystalline, then we know that the bonding might be issue, the uptake, hydrogen storage might be an issue. So we have to find out some a compromise between these extremities. Of course, we are yet to study on that, and most possibly these will be our next experiments. Then pore shapes and material activation. So material activation also, we need to remove all the organic materials, moistures and everything. So for that, material activation should happen at a low temperature. So perhaps we can add some catalyst and we can decrease these temperatures. So how this porous material now, how these properties can be exploited, that is what I'm going to explore in the upcoming slides. So first of all, as far as porous materials are concerned, depending upon again all the parameters, they can show up to a high surface area up to 800 meters square per centimeter cube. So this is a very high area, and this is happening. You can see here, this is the pore is starting to form, and once the process goes, you see like fractal like structure. So this will go on, and again on this the pores will happen. So the etching can be controlled, and we can control the direction as well. It can be perpendicular as well as parallel. Perpendicular means like this to the substrate, and parallel means this is horizontal direction, and which is parallel to the substrate. So this porosity can be controlled between 30 to 80, and of course then we are controlling the surface area, and that will lead the hydrogen concentration. So you can see here in one of the very early papers, porous silicon hydrogen concentration is already given. And this is something interesting. At this point, suppose we can have a porosity more than say 70% or so, the hydrogen uptake is non-linear. This is happening because now as the porosity is high, the pore walls are very thinner, and thus the hydrogen diffusion inside the material is increased. And now apart from that, because the media is porous, the air ventilation is quite good. So that's why it will allow the heat exchange, and as I've said, the facile diffusion. So normally this absorption happens mostly because of the physical absorption. However, so that's a physical option, but there is a possibility that at higher temperatures, some little bit chemisorption can also be possible. But moreover, you can say the physical option is the dominating mechanism over here. Now, apart from this, apart from the surface area and porosity and all that, it also depends on how bad the material is. So in solar PV, we were talking about the material should be good, right? The crystallinity should be higher, the defect should be lower, but it is exactly opposite over here. We want more defects, because more the defects, that becomes the sites for hydrogen to go and sit. Also, we require certain dopants which will add the defects and adsorption centers. Okay, so also if we dope it with certain materials which can work as a catalyst, this is going to help in dissociation of the hydrogen, and it will help in hydrogen ion adsorption. So this theoretical limit for porous silicon is shown as about 7.1%. So now this was porous silicon, and already at that time in 2012, this particular paper, I was working on silicon quantum dots for solar PV, and then we got this idea that we can use it for quantum dots, because now quantum dots has got added advantage compared to porous silicon, that you have got much larger surface area, right? Because now it's a 3D material, just a 5 nanometer dot what we have. Porous silicon, there are certain there is some bulkiness is still there. So we went for the nanoparticles, or making the quantum dots, as I have explained in previous slides. So these particles were ranging in somewhere in between 8 to 20 nanometers. And we run a very preliminary experiment at that time. Of course, remember 2010 or something, the hydrogen storage was not that mainstream area. And of course, silicon was not at all the mainstream area. Still, the hydride, metal hydrides, and ammonia borane and all those materials were quite, hit materials. So at that time, we showed about at 120 degrees Celsius and roughly at 10 bar, the uptake was about 2.25%, where the small plateau was seen. But unfortunately, as you must have seen in magnesium hydride also, the clear plateau is not formed. And of course, the answers were not known at that time. And right now, to be precise, we are working on that. So anyway, here what we saw was at room temperature, even the pressure was, uptake was about 1.4%. So this was the major, advantage of that hydrogen uptake is taking at such a low temperatures and low pressures. And of course, this hydrogenation is increasing the strain. That is what we determined from the Raman lattice, because now your hydrogen is diffusing inside, and also the pressures and temperature is inducing the strain in the system. So obviously, the crystallinity reduces during this hydrogenation, and about 0.2% crystallinity was reduced in this. So of course, it would be interesting to see how this material goes, how this material behaves when we go for the cyclic studies of uptake and release of the hydrogen. So and then how we made sure that the hydrogen was absolutely absorbed, that after hydrogenation, when we remove the material, we took it for UV visible, and in UV visible you can use the top plot. Unfortunately, I haven't prepared that slide, so you can prepare a top plot, and from the the linear part of that top plot, you can extrapolate it, and that will give you the band gap. Now, this particular technique is a very common technique in semiconductor industry to check the band gap. So obviously, the main reason of band gap increasing there was hydrogen passivation. So we obviously expected, and this is what we saw here as well. So after the hydrogen uptake, the material had a very increased band gap from about 1.4 to 1.6. So that was a huge increase in the band gap, which implied that particles are taking the hydrogen. Then simultaneously, one of my collaborator was working on ammonia. And at that time, we thought that why not to use, just to test, why not to use these silicon nanoparticles as a catalyst in ammonia borate? Why and how, we were not known. So because it was simply, a hunch. So we used those silicon nanoparticles, same silicon nanoparticles for ammonia borate. And then again, we had some interesting results at that time. So we always want the induction period in hydrogen, storage materials to be low, so that the reactions are faster, kinetics are faster, your wet percent release is faster, right? That is what we expect from the battery as well. We want the battery to be charged faster, as well as it should release as fast as we want. Okay, so here when we introduced silicon nanoparticles, the induction period of just ammonia boron was reduced. Of course, when I say ammonia boron plus silicon, we used ball milling for this, and we made sure that a proper alloy is not alloy, I should say mixture, homogeneously mixture is made. So here the induction period is reduced to almost nil at high temperatures. And as far as the increase of amount of gas released from ammonium boron, because ammonium boron works on a principle of decomposition over here. So whatever the hydrogen already inside ammonia boron, it has to release it after decomposition. So that hydrogen gas released was also increased by about 1.2%, which you can see in almost the graphs of 90 and 110 degrees Celsius. Of course, at higher temperatures, the kinetics were very much similar here. And apart from that, the activation energy reduced by about 30% or so, from 47 to 32 kilojoule per mole. So of course, it was very interesting results. We again got patent on this, but unfortunately we stopped working on that in somewhere in 2011. And then last 2-3 years or so, again I thought that I should take up the silicon and the derivatives for hydrogen storage. So again, as I have told you, the 3-4 structures what we had, so we have already studied those structures, and then we thought that now it is better time to go for the application, hydrogen storage as application. So we renewed the study. So we started to look at all the aspects from our very little knowledge at that time, and again look at it and find out, start from the basics and understand how exactly the things are happening. So we started with some fundamentals like the BT measurements. Now, as far as BT is concerned, it's a technique to it's a gas absorption measurement. So you can determine, first of all, the surface area. That is what it is largely preferred for porous materials. Of course, gravimetric analysis is one easy way to measure the porosity. But gravimetric analysis, because of the large error in the weight measurements, it can give you error of about 5 to 10%. But BT is very precise because it works on the gas absorption principle. So not only surface area, you can also determine the shape and distribution of pores on the surface. So you can see here in the diagram, we have got about 5 different adsorption, desorption curves. Of course, hysteresis loop is when you combine the two, and these nature are to 5 distinct natures you have, and those represents the 5 different different pores over here. So we thought that we will use this BAT and understand how exactly the morphology is changing and how ultimately it is going to affect the gas adsorption. Because in BAT we normally we use nitrogen or argon, but later we can use it hydrogen by suitable changes in the models. So of course that is what we are doing currently. So here from the hysteresis loops, we can determine the texture and geometry of the surface. We can determine pore size, shape, its distribution, and how it ultimately affects affects the adsorption, desorption, and how the interaction between the two changes. So these are the 5 curves that hysteresis types we can have. So you can see pore structures. H1 has got cylindrical structures and H2 has got in-bottle structures. This is the normal structure you will get in porous silicon. But when we went for porous silicon nanowire especially, we saw that, and especially at low resistivity wafers, 0.001 to 0.002 ohm centimeter, the things were quite different. The response of the material was quite different as to the high resistivity structures. There we found out that we got H3, H5 and H5 hysteresis, where now your nature of the pores were absolutely different. So H1, H2 where we can say typical pores, but whereas for H3, H4, H5, we had very nanopores over here, groove type, slit type, and inverted types of pores. So here, these are the steps, what you say, in table, you can say, this is what happens when we expose a gas to a particular porous silicon medium. And this is the diagram, the first one. Just a second. Okay, so these are the diagrams I'm talking about. So these are the 6 steps, and this is the 6 levels of interactions between the gas and the porous media. So first you can see that the monolayer is forming only on the surface. The first hydrogen atom is going and sticking. Of course, it's a physics option. And then on that, the layer formation starts. So here your interaction is between silicon and hydrogen. But whereas here your interaction is largely dominated by hydrogen. And then this goes on increasing. And of course, we know that this multi-layer formation will be limited by what is the pore size. So that comes into picture. And of course, pore size distribution is the another dimension to it. So when we increase the pressure further, there is something interesting happening, which is called as the capillary condensation. So here the gas liquefies, almost it behaves like a liquid, and then in that phase it retains in there at high pressures. And once you start that decreasing those pressures, that pores will start evaporating, the gas will start evaporating, and again you will come back to multi-layer film and back to the monolayer film. So normally in H2, as I've said, we get the ink bottle structure. This is what I have shown over here. So in ink bottle structure, something interesting happens. So these are bottles. So the hydrogen is stored as if we are storing something in bottle, right? But the problem is here, problem is the bottleneck, and literally the bottleneck. Okay, so what happens is, inside there is a large gas, and then you have got a very small area for that gas to come out. So this is what changes the shape a little bit for that. So capillary condensation is one very important parameter, and because of that the desorption is going to fail, because gas can go in easily. However, when it comes out, there is the rate of desorption is different. So what happens, we can also find out from this BT what is the coverage area of this. So how much gas exactly is covering how much surface. Okay, so see, this is the single layer adsorption. So you can see those black dots which are covering the various pores, and this BT constant can be determined from this particular graph. So it will be slope upon intercept +1. Now this C is basically used to find out theta C, which is the fraction of surface. So it tells you, of course, it's in percentage. So how much percentage of the surface is covered by the particular molecule over here. So of course, as C is infinite, that is the highest possible adsorbate surface interaction. So in practical cases, what we want, that C should be as high as possible. And you can see that this C is determined in a very small P by P0 ratio, 0.1 to 0.3, where you will have a monolayer formation, because that is where the surface will be covered. Once the dual layer starts, multi-layer starts forming, then you are not actually covering the area. So that's why this is the region what we use. So now I'm going to show you 2 isotherm types. One is for silicon nanostructures for 0.01. That is what we call it as high resistivity. So we will have total 6 structures: porous silicon, silicon nanowire, and porous silicon nanowire for high resistivity and low resistivity. And you will see that although the process is very simple, process is very same, just by changing the resistivity, the whole scenario changes over here. And then resistivity also becomes one very important parameter to be considered for the applications, which is not really reported over here. So you can see the BT constant, that is C, is highest 20 in porous silicon, and it gives us about 82% of the surface area is covered, and pore diameters are about 9.53. But moreover, you can see that pore diameters are same, and that is what you see from the pore PSD diagram. So this is the graph for PSD. The volume of the pores is moreover the same, and they are confined to a very similar region over here. So we can say that the homogeneous pores are formed over here. And we can see that we can in the VT curves, we have got H1 and H2. So we get the cylindrical pores and inguinal pores. It means that the perpendicular vertical etching is the dominant over here because of the high resistivity in this case. So this is very less prone, in other sense, less prone to the horizontal etching. So that's why the small arrow I have shown. So it will be vertical etching, and that's why you get the cylindrical pore straightforward, or you get a what you call it as ink bottle type of pore, which I have shown earlier. But now when we change this to 0.001, everything changes, and we get H3, H5, H4, and H5 isotherms. And apart from that, the pore size distribution is also changing over here. So you can see here it is bit broad, but in a very small domain, right? In between 3 to 12. For this red one is the porous silicon nanowire. For porous silicon, it is very confined as what we have seen in moreover in the previous one. And for silicon nanowires, the things are very broadened. Now, then the porous silicon still is giving a very high VT constant and 86% of the fraction. Of course, it is not that far from the other two, but that little bit percentage is quite what, differentiating. So H3 is a tapered plate-like pore, H4 is a narrow slit type of pore, and H5 is inverted shape pores. Now, this is happening because of the parallel etching effect, because now first the etching starts perpendicular, and then the horizontal etching is also dominant, because once it starts etching, here the resistivity changes, and once this resistivity is low, it has got other path. This is like a resistance. So suppose this resistance and this resistance for etching is now equal, then obviously you will have etching in both the directions. So that is what happens over here. Your resistance here fails, it becomes equivalent to the horizontal, and then the etching rates are more or equal. So now you have got etching in all the directions, parallel as well as the perpendicular etching. So from this what we can conclude is that porous silicon shows good adsorbent because it is showing the better fraction surface, and it has got a better interaction with the hydrogen. Now, other thing to determine was which species are available after we expose it to after we make this silicon hydrogen, because surface modification, surface activation, this is one important parameter. So that's why we thought that we will go for NMR spectroscopy and the FTR spectroscopy. NMR and FTR moreover very relative. Of course, we are digging more into NMR spectroscopy. So let me tell you what are possible things, and of course we have done some of them. So it can determine the content and purity of the sample in its molecular structure. So you will get, because of the effect of magnetic field on the nuclear spins, depending upon what type of NMR you use and what frequency you are going to use, you can find out the bonding determination at the surface. So majorly this bonding would be hydrogen, and apart from that, the oxygen as well, because these are the two major species we have got on the surface. So it can determine the various structures. Elemental analysis can be done, and here, because it's silicon, we have to use a solid state NMR because silicon is solid. Normally in chemistry and chemical, they would be using liquid state NMR, where your isotope will be very different. So 28 is normally the silicon weight. So here we are using 29 silicon. So this higher surface area will be providing sufficient nuclei that will give us a sufficient result, a sufficient signal to noise ratio for this. So a small difference in this 28 and 29 number is going to give us the magnetic spin over here. So as I've said, apart from hydrogen, we can also determine the reaction with the oxygen, because when there is no hydrogen, there will be oxygen with the silicon. So hydrogen and oxygen are very very much silicon is affinitive to that. So we have to study whether there is a presence of oxidation or not, because if oxidation is there, we have to remove that oxidation. So we have to have some surface treatment for that. So we can go for different isotopes. 28 would not be good, so 29 is the most favored isotope over here. So there is one half spin, which is one spin is different, and that is why it can show the magnetic moment over here. So spin coupling of one hydrogen would be shown towards the 29 silicon. So in this we get the chemical shifts. So depending upon what species is sitting on the surface, you will get a chemical shift, and it has got a very wide chemical shift range. So this is very useful to determine the chemical environment. So these are the typical shift range which are reported. So you can see for silicon itself, depending on crystallinity, it can be 60 to 85. Silicon hydride species can be from 50 to 100 or so. Then we have got oxides and some hydrogen atoms or some organic radicals. That is why it is R, which are bearing some functional groups. So the point is, the NMR is one of the most sensitive spectroscopy for determining the surface species. So initially we use this trimethyl ethane for the standard to determine the chemical shift. So with respect to this tetramethylsilane, we are going to determine the shifts. So this is what we observed. And then, of course, you get only one curve over here. So I think it is given by the black one. Okay. So this black one is going here and coming down and again fluctuating, right? So of course, in black, you cannot determine what exactly is there. So what we did is, we fitted this, we deconvoluted this into eight different graphs. Okay, so that we get a maximum peaks which are hidden inside. And once we did that, we found out for every every structure, we are getting some species which are related and which I have tabulated over here. So this confirms, so right now our objective is just to confirm the surface bonding. Other structural studies we are still doing, and we have confirmed here that what different oxide and hydride species are sitting on the surface. Now, with this knowledge, we also wanted to test indirectly the nature of the surface. And one simplest way, perhaps, is the hydrophobicity of the silicon and derivatives. So with the water, we have tested what is the contact angle it is making with the surface. So this hydrophobicity can be divided into three: normal, then super hydrophobic, and super hydrophobic, and similarly the other way around. So in pristine silicon, which is clean, we get about 90%. But when we go for porous silicon, now some oxidation is happening, and because of that, you can see the hydrophobicity is decreasing because of the oxidation. But when we go for sintered porous silicon, it is becoming a super hydrophobic structure. So this is like a lotus like effect. And when we make silicon nanowires, similarly, it is showing the hydrophobic nature. So obviously, this is happening because of the absence of hydrogen over here. So then we thought that why not to use certain easy methods and treat the samples with as it is, make it old, so that natural oxidation will occur, and then rinse it with HF acid and DI water. Okay, so when we do that, this is what the phenomena is happening. So you have got silicon bonded with hydrogen and hydroxyls and hydrides, and then when we start treating this with excess amount of water, the silicon, what you say, this activity is replaced by the extra H2O that what we have, and then you get this silicon bonded with hydrogen and the OH minus, and H plus is released. And with this again, this OH, it will absorb one hydrogen, and the other hydrogen will release with get attached with H plus, and hydrogen will be released. Okay, now this is very interesting, because if we treat our porous silicon with water, what we are going to get is hydrogen. So this would be the easiest desorption what we can have, that too at the room temperature. So this method can be useful for what you say, removal of hydrogen from what you say, where the porous silicon, where, or the silicon nanostructures where hydrogen is absorbed. And once it happens, then these OH structures will also get removed, silicon and oxygen, silicon bridge is formed, and your hydride is also reduced. So these are the reactions associated with that. Of course, just to confirm these reactions reported, or the phenomena reported, we ran our samples through FTIR, and you can see that the black sample is the fresh one. So when we fresh, and this is the old one. Okay, and both we are treating with HF and DI water, because that is that will contain oxygen. HF doesn't contain oxygen, and then we will treat it only with HF, just to see the effect of that oxidation. And you can see that black, it has got quite oxide, oxide has been formed. Whereas when we go for the HF plus DI water, HF is going to eat this SiO2. It is going to remove this oxidation, and of course it doesn't remove completely because of the presence of DI water. However, when we use only HF wash, it removes that oxide completely. So this is how we can, change or modify the surface of the porous silicon, or for that matter any silicon nanostructure, and we make sure that there is no oxygen present on this, and the surface is easy for activation, and the activation required would be for lesser time, so we can save some energy over there. And apart from that, when we have got only HF wash, oxide is removed, and then it increases the hydrogen capping, and this is good for us, because this is going to attract, because now there is nothing sitting on the surface, so this will attract the hydrogen when we give the opportunity. Otherwise, if we don't put hydrogen, again it will slowly attract the hydrogen, and again it will become silicon dioxide. So oxygen is, anyway we don't want oxygen, so in the hydrogenation, because it acts as a poisoning, it acts as a poisoning effect in the material. Now we have to study this oxidation bit further, so we also went for TGDSC. So quickly I will run through this thermal analysis. So thermal analysis is where you control the temperature or heat flow onto the material. So you can find out several things: stability, your thermal composition, decomposition, oxidation, these exothermic reactions, rate of those reactions, what energy you require for that, whether there are any moisture or volatile content of the material, is there any decomposition happening of the material. So there are so many ways of doing it, and so many techniques are there. But roughly it is done in furnace with some thermobalance, and you have a program temperature for this, and you have to acquire the data. So in two methods we have followed: TGDSC, so thermogravimetry. So this is to investigate whether there is a loss or gain in the weight of the substance over the time and temperature. So isothermal mode is weight change as a function of time, and scanning mode is a weight change as a function of temperature. So this weight loss or gain, both will give you some idea. So loss will give you decomposition, that is the breaking of certain chemical bonds, evaporation of certain materials, or reduction of certain species, and then the desorption. So if any gas is absorbed, if it is getting dissolved, and weight gain is largely due to the oxidation. So this is the interaction between the if any oxide is present. So that's why you should be careful in such a experiment that there is no oxygen present. So it is normally done in inert temperatures. So based on this, we get certain curves, and from that we can understand what is the nature of the, from this nature of the curve, we can understand what exactly is happening. For example, A is a flat line, so there is no change in this. But whereas B, there is a change and then it remains constant. Sorry, yeah. C is the single stage decomposition. D is multi-stage decomposition. Normally this happens when you have got what you say, you decrease the size of the particles. E is similar to D, but then of course the parameters of TG is the hitting rates, at what rate you are hitting the substances. So the plateaus would be different in this case. F is atmospheric reaction, normally for oxidation. So you can see that there is a mass increase in here. G is also similar, but however, after certain time, this whatever the surface species has been formed, it decomposes further, and that's why mass is again lost at very high temperatures. Then TG is normally coupled with DSC. This gives some other information like the measure of the melting point, the glass transition temperatures, a degree of crystallinity and oxidations and all that. So of course, there are certain industrial applications in case of understanding the heat and aging effect on the samples, the ideal temperature for manufacturing process, because melting point, that is what you want to determine, and identify the impurities which would affect the long-term performances. So this is the typical DSC curve you get. So transition temperatures are there, exothermic peak where your heat flux goes down, and endothermic flux, heat flux gains on y-axis, and of course x-axis is the temperature. So each peak corresponding to some or other heat effect, and the glass temperature that I haven't mentioned. So the materials are converted here. So amorphous materials are normally converted into brittle or glass-like structures. So that will occur quite at low temperatures. So these are the TGDSC characterizations. So the hollow legends are for the DSC, whereas so these ones are for TG, and these ones are for the DSC. Okay, so glass temperature occurs somewhere as at 114 and 217, and then endothermic peak is at about 292. So this is where the hydride bond starts breaking, and as I've said, silicon H, SiH2 bond starts breaking. And then unfortunately in our sample, thin oxide layer started to form, and later we came to know that there was some oxygen present because of the leak in the furnace that what we used for the TGDSC. So that's why you see that there is some oxidation present over here. Anyway, so the point is the above surface, above 700 degrees Celsius also, that is the phase 3, what we call it as, there the restructuring occurs, which I've talked about. So that's why the restructuring or sintering temperature was about 800 to about 1200 degrees Celsius or so. In the second region, moreover, it's oxidation, and because of that, the heat flow is reducing over here. And at 876 or so, some of the hydrocarbons get lost from here. Similarly, we carried out this TGDSC for the sintered nanowires. So sintering I have explained, and there we found out some very interesting phenomena, and that's why although this is a bit related to silicon photovoltaics, but still I'm adding it here. So you can see some interesting part happening initially. So this is the pristine silicon nanowires, where we get the silicon nanocrystals of about 1 to 3 nanometers. Okay, but when we started increasing the temperature, so at about 1000 degrees Celsius, the crystal size increased to 4 to 6, and we got it highest at around 7 nanometer at the temperature somewhere around 1100 degrees Celsius or so. And what we found out when we fit the curve, we got the highest point as the 1032, and this is the critical temperature we found out. So this is the different application altogether we have done from this TGDSC. That's why I'm showing it to you. So at 1032, we found out that this is the critical temperature that should be applied, where after that, you are going to, again lose your silicon nanocrystals, or again, you are going to lose your pores, and pores will start shrinking in this case. And the highest highest diameter size of the nanocrystal, what you can find out will be somewhere around 5.2 nanometers or so. And we have fitted the curve, and we have also found out how exactly you can optimize that. So if you want to sinter the nanowires and you have to tune the nanocrystals, you have to consider these parameters, and you can find out this. So this diagram is what it explains. So initially you have got a core shell structures, as I've shown in the previous slides. So these small nanocrystals are going to merge. They will become larger nanocrystals, and you get a core shell structure, but with a so you get a single nanostructures at about 10332. However, when you start increasing the temperature again, it falls back to the core shell structure. So again, you get some amorphous content on the top, and it loses the crystallinity. So sintering increases the crystallinity at certain point, and after that it decreases the crystallinity. That is what we have found out. So now coming back to our hydrogen, as I've said, there are two types of etching happening over here. So in porous silicon, we have normally the vertical etching. So you can see vertical etching, but when we decrease the resistivity, we get the horizontal etching as well. And this creates new pores as well as the widening of the pore. When we use mesh technique for nanowire formations, this is what is happening, and bundling occurs of the nanowires, and this is due to the capillary force. You must have seen, these nanowires coming together at the top end, and of course the structural change is that some etching will be done, and you will get a different length of the nanowires as well. And then you can lift this off using anodization, and there will be certain structural changes during this anodization as well. This is the second method where we use porous silicon substrate as well. So as now you can see here, here the silver nanoparticles has to dig bulk silicon, which is very solid, but whereas porous silicon substrate is brittle. Okay, so here the etching rate is faster, and here what happens is it is, both parallel as well as perpendicular is dominant, especially in a low resistivity substrate, whereas we never found out it in high resistivity substrate. So although the mechanism is same, the etching is occurring, but the intensity of etching differs in the different resistivity, and that changes the morphology and the pore structures, pore size distribution, whatever we have discussed. And of course, when this is changing, your surface is getting exposed to the new atmosphere, and your surface modification also happens simultaneously. So now, as far as hydrogen storage is concerned, and for that matter, suppose we are going to use these structures for, say, any application. The problem is we have got hundreds of parameters, not to exaggerate, and we have got various structures. Okay, so how we can, optimize, how to select this, and that we have solved with something called as a rank matrix. So to optimize silicon nanostructures for a particular applications, we can rank the structures. So for example, this is the case of hydrogen storage. So we have divided various parameters into 3 different categories: high impact, medium impact, and low impact, which will be on the gas, adsorption, desorption. So of course we know that covered area, surface area, hysteresis type, these are high impact areas. But however, we know that their values for respective 6 structures. So remember, this is high and this is low, otherwise the structures are same. Then we have got medium impact parameter like pore diameter, fabrication cost, because that is also important. Otherwise, if the cost is too high, the effectiveness will not be there. And then porous size distribution, medium impact, and low impact was how much volume was exactly adds up. So we have given the points and we found out the total points and the rank. And what we found out that, the porous silicon doesn't matter what is the resistivity. It's a good competitor over here for hydrogen storage. Okay. And why it is interesting, because we went for porous silicon nanowire, so that we increase the surface area, so that we will have a better material for hydrogen storage. But in fact, if you see, the porous silicon nanowires are failing miserably. Of course, only this porous silicon nanowire was better. 79 was the score, 70 was the score, just one below this 71. So 1, 2, and 3 silicon nanowire was the most, only silicon nanowire was the most hopeless, and porous silicon nanowire was the worst ever. So the point is, there is no point in putting more energy and time to make the porous silicon nanowires. We should be satisfied with porous silicon, or if we want, really, we can go for porous silicon nanowires. But now this needs to be checked with the hydrogen storage, and of course that is what we are currently working on. So this is the cobweb for that. So we can rank these based on the parameters. And again, of course, these are our perceptions. Depending upon your applications, you can always change the weightage given for the parameters. You can change the impact levels. And of course, you will get a very different rank matrix in this case. So what is the future scope, or rather what we are doing? So of course we have studied the surface area. We found out that when we clean the surface area, there is a very hydrogen capping would be increasing after we chemically modify these structures. And once we modify it, we can lift it off, grind it, make it powder, try it to remove any moisture or something, and activate it. Okay, so once activation is done, there will be only silicon nanostructures, and these powdered silicon nanostructures can now be used for the hydrogen storage. So because these are very much affinitive towards hydrogen, we feel that these structures are going to be very useful for hydrogen storage. Now, so that was all about hydrogen storage. Of course, as far as porous silicon is concerned, we require desorption. Of course, the easiest way is just heat it or increase the pressure. Okay, so you can manipulate the pressure or temperature so that there will be thermal dissociation of the silicon hydride bonds. And as I've said already, somewhere between 150 to 400 degrees Celsius or so, the different bonds are going to break, and then you can get the hydrogen back. Another thing which I discussed when we talked about the treatment of porous silicon with water. So when you put it in water, because of the reactions, you are going to get hydrogen released. The other renewable or sustainable way could be illumination. So you can put it in the light, you can concentrate the light, and you can rather put some catalyst so that this absorption of photons becomes higher, becomes faster. So this is where we think that the silicon nanowires and porous silicon nanowire will give an edge. Okay, so that is what we have to study it, and then in this case we can increase the speed. Currently it is slow, we can increase it, and at a lower power expenses for that. So that is all from my side. So thank you very much. So this was all about whatever we are doing and whatever we wish to do. Of course, I thank very much Professor Ankur Jain for his invitation, and of course my student contributors Mihir, Ramchandra, these are PhD students, and others are JRFs and the MTech students. And then of course our DST IITB energy storage platform, where we six are working together in a team. So of course there is a lot of help from them as well for characterization and everything, because we use every other's instruments, and without that I don't think many things are not possible. So thanks to our collaborators as well, all the collaborators in fact, apart from this as well. So thank you very much. So if there are any questions, I think I can take the questions.
Thank you so much, sir. It was really a very interesting session, and we have received 2 questions from our participants. The first question is, sir, how can we compare hydrogen storage capacity of silicon nanostructures with alkali metal hydrides?
The comparison, there is only one parameter. How much is the hydrogen uptake? That is the first parameter, simplest one. Okay. Second thing, as I have said, of course, at laboratory, we can do many things and we can show that, 2.5%, 5% and whatnot. But the most important parameter is when we put it for practical application, at what temperature and pressure it will work. Okay, at what temperature, pressure it will adsorb and desorb. So these are the other 2 parameters what we have. So as I've said, I think magnesium hydroxide hydride gives around 5% or so. Carbon, someone asked, it also gives around 4%, 5% or so, because carbon is a porous material. That's why I'm telling you. Then ammonia borane is also in a very similar range. So these are the percentages. So right now people are talking only of the percentage, but later I think we should be also talking about temperature and pressure operating conditions.
Thank you, sir. That was really an insightful answer. The next question we have is, can we utilize silicon nanostructures for any other applications like selective adsorption of heavy metals and contaminants like?
Yes, in fact, yes, we can. Definitely we can. We can rather, in fact, of course, this is not the part of this presentation. We had one project where we were detecting chromium using a biosensor, where we activated porous silicon with horse ride enzymes and other enzymes as well. So porous silicon has been already proven as a very good detector, very good sensor, also in biosensors. Okay, so yes, definitely that is possible, but for that we have to use enzymes or another activating agent, so that it would be efficient. And in sensors, one important property what you should have is the discrimination, because let us say if you are talking about heavy metals, chromium or lead, both are heavy metals, so there should be some distinction when it gives the signal. So for lead as well as for chromium, your sensor should not give the same signal, right? So that discrimination is based on that is where the enzymes or these bioagents comes handy. They can give you, say, different results even for the same concentration of the very similar, let us say, heavy metals.
Thank you so much, sir. Thank you so much for taking out time from your busy schedule. On the behalf of Gyan Vihar University, I extend hearty thanks to you, sir, and all our participants. They are also expressing their gratitude towards you, sir. So thank you so much. Thank you so much, everyone, for joining the session. With this, I declare end of the session too. Thank you so much, everyone.
All. Thank you, Dr. Srivastava, and also the audience for patience listening. Thank you very much. It was a pleasure.
Thank you, sir.